In this video, we're going to look at several examples working with geometric series. Recall that a geometric series is a series that can be written in the form sum n equal 1 to infinity of a times r to the n minus first power. If we write out the first several terms of our geometric series, we'll obtain a plus ar squared plus ar cubed, and so forth. Each term is found by multiplying the previous term by the number r, which we call the ratio of our geometric series. A geometric series will converge whenever the absolute value of the ratio is less than 1. In that case, we can find the exact sum of the series using the formula a over 1 minus r. Keep in mind that this formula a over 1 minus r only applies to our geometric series when our ratio has an absolute value less than 1. If the absolute value of our ratio is greater than or equal to 1, then our geometric series is going to diverge. So in order to determine convergence or divergence of a geometric series, we simply need to determine the value of our ratio r and determine whether it has an absolute value less than 1 or greater than or equal to 1. If it's less than 1, then we can use the formula of a over 1 minus r to actually compute the sum of the convergent geometric series. In this example, we want to find the exact value of the series from n equal 1 to infinity of negative 3 to the n plus 1 over 4 to the n minus 1. We should recognize this as something that looks a lot like a geometric series, but also note that as written, it's not given to us in the appropriate form. A geometric series must be written in this form n equal 1 to infinity of a times r to the n minus 1. And so what we're going to need to do first is to rewrite the terms of our series to be in this appropriate form. And so we can do this in a couple different steps. We can first look at the numerator. We have an exponent of n plus 1. In order to get the exponent of n minus 1 that we want, we need to reduce that exponent by 2, which means we have to break off 2 copies of negative 3 from that product. And if we do that, we get negative 3 squared times negative 3 to the n minus 1. And now we have the n minus 1 exponent that we want. And we already have 4 to the n minus 1 in our denominator, so we can just leave that as it is. So now we can rewrite this. Negative 3 squared will be the number 9. It'll be a positive 9 since we're squaring the negative number. And the other two terms, since they have the same exponent, we can actually combine them using properties of exponents into negative 3/4 to that common exponent of n minus 1. And so we've rewritten our series as the sum from n equal 1 to infinity of 9 times negative 3/4 to the n minus first power. And this is exactly what we needed to do to match our geometric series form. We have an initial value now of 9, and we have a ratio of negative 3/4. Now we can determine everything that we need to know about this geometric series by looking at these values of a and r. First, we have the absolute value of r, which is the absolute value of negative 3/4, which is positive 3/4. That is a value less than 1. And so that tells us that our geometric series converges, because our geometric series will converge whenever the absolute value of the ratio is less than 1. In this case, we know that the sum is given by the formula a over 1 minus r. And so for this particular series, we can substitute these values in. So a is the number 9, our initial term, and r will be negative 3/4. So we'll have a denominator of 1 minus negative 3/4. We can, of course, compute the denominator there. Will be 1 plus 3/4 will be 7/4. And so we have 9 over 7/4, which we can compute to be 36/7. And so the exact value of the series that we were given here will be the fraction 36/7. If you'd like to try a similar example, find the exact value of the series from n equal 1 to infinity of 5 to the n over 7 to the n plus 1. You can resume the video, and in a few seconds, you'll see the full solution. Our first step is to rewrite this in the standard geometric series form, a times r to the n minus first power. To do that, we break up our numerator 5 to the n as 5 times 5 to the n minus 1, and we break up our denominator as 7 squared times 7 to the n minus 1, and that will give us both terms to the n minus 1 power. We then group everything together. We have a constant term of 5 over 49. That'll be our initial value a. We have 5 over 7, 5 sevenths to the n minus 1 power. And therefore, since that has an absolute value of less than 1, this series will converge. And so we can use our geometric series formula of a over 1 minus r, and that will give us 5 over 49 divided by 1 minus 5 sevenths, which we then can simplify to be 5 fourteenths. So the exact value of our series from n equal 1 to infinity of 5 to the n over 7 to the n plus 1 is 5 fourteenths. In this example, we want to determine whether the series from n equal 1 to infinity of 2 to the 2n times 3 to the 1 minus n converges or diverges. In order to do this, what we're going to do is use algebra to rewrite our series term, 2 to the 2n times 3 to the 1 minus n, in the standard geometric series notation, a times r to the n minus 1. Once we get our term written in this form, we can simply look at the number r and, based on that number, determine whether the geometric series will converge or diverge. So we're going to use some properties of exponents to rewrite this given term in the form a times r to the n minus first power. We can start by rewriting 2 to the 2n as 2 squared quantity to the nth power. For the second factor, 3 to the 1 minus n, what we might notice is that that exponent is the negative of what we want. We want n minus 1, and what we have is 1 minus n, which is actually the negative of n minus 1. And so this tells us that one option here would be to move this term to the denominator. And by doing so, we have to make the exponent negative. And so moving this to the denominator gives us a denominator of 3 raised to the negative quantity 1 minus n power. We can clean this up a little bit. In the numerator, we now have 4 to the n. And in the denominator, we have exactly what we want, 3 to the n minus 1. So we have our n minus first exponent. In the numerator, we have 4 to the n, and we want 4 to the n minus 1. And so we can break this up as 4 times 4 to the n minus 1, all over 3 to the n minus 1. And now we just need to group like exponents, and we have what we are looking for. We have a initial value of 4, and everything else can be written as 4/3 to the n minus first power. Well, once we have it in this form, we see that we have an initial value a of 4 and a ratio of 4/3. And here, the absolute value of 4/3 is just 4/3, and that is greater than 1. And since we have a ratio that is greater than 1, we know that our geometric series is going to diverge. And so the series from n equal 1 to infinity of 2 to the 2n times 3 to the 1 minus n diverges. If you'd like to try some similar examples, you can pause the video and determine whether the following geometric series converge or diverge. First, the series from n equal 1 to infinity of 3 pi times 7/3 to the n plus 1. Then the series from n equal 1 to infinity of e to the 2n. And finally, the series from n equal 1 to infinity of 10 over 3 to the n. You can resume the video in a few seconds to see the full solutions for all three series. The first series can be rewritten to have a ratio of 7/3. Since the absolute value of 7/3 is greater than 1, that series will diverge. The second series can be rewritten with a ratio of e squared. And again, since that absolute value of that ratio is greater than 1, the series will diverge. And the third series can be rewritten to have a ratio of 1/3, and the absolute value of 1/3 is less than 1, and so the third series will converge. In this example, we want to use geometric series to write the repeating decimal 3.12 repeating as a fraction. To do this, our first step is to rewrite our repeating decimal as a series. In order to do this, we're going to utilize the fact that 3.12 has this common period of 1, 2 that is repeated over and over in the decimal expansion. And so this means that we can rewrite 3.12 repeating as 3 plus 0.12 plus 0.0012 plus 0.000012, and so on. We can then rewrite each of those decimals as fractions. So this will be 3 plus 12 over 100 plus 12 over 10,000 plus 12 over 1 million, and so on. We can then write this as 3 plus 12 over 100. And for each of these other terms, we can rewrite them as with a factor of 12 over 100. So 12 over 100 times 1 over 100 plus 12 over 100 times 1 over 100 squared, and so on. So now, for a moment, we're going to ignore the 3 in front. Ultimately, we're just going to add 3 at the very end of our problem. So we're just going to have 3 plus something here. What we notice is that everything other than the 3 is a geometric series. This particular series will go from n equal 1 to infinity, and we'll have our initial term of 12 over 100. And our ratio, we will see, is 1 over 100, because what we're doing in each term to get to the next is multiplying by 1 over 100. And so here we have a geometric series of 12 over 100 times 1 over 100 to the n minus first power. And so this is a geometric series. Our R value, our ratio is 1 over 100. This has an absolute value less than 1. And so this is a convergent geometric series. And so we know how to find the sum of convergent geometric series. And so we do that and add to 3 to find the fraction for our repeating decimal. Continuing on with this calculation, we're going to have 3 plus the value of a, which is 12 over 100, divided by 1 minus r, which will be 1 minus 1 over 100. So this is just the particular geometric series we have here, and utilizing our a over 1 minus r formula. And we can simplify all of this. This will be 12 over 100 divided by 99 over 100. So we have 3 plus 12 99ths. And when we add 3 to 12 99ths, we get the fraction 309 over 99. And so here is a fraction that represents our repeating decimal of 3.12 repeating. If you'd like to try a similar example, pause the video and write the number 1.204 repeating as a fraction. Resume the video and see the full solution in a few seconds. We can rewrite 1.204 repeating as 1 plus 204 thousandths plus 204 millionths plus 204 trillionths, etc. We can then rewrite each of those terms as 204 over 1,000 times an appropriate power of 1 over 1,000. This allows us to rewrite all the terms except for the one constant in front as a geometric series. So we end up with 1 plus the sum from n equal 1 to infinity of 204 over 1,000 times 1 over 1,000 to the n minus 1 power. We can use the geometric series formula with a being 204 over 1,000 and r being 1 over 1,000 to see that our decimal becomes 1 plus 204 thousandths over 1 minus 1,000th. This simplifies to 1 plus 204 over 999. And adding the 1 in to get a formal fraction gives us 1,203 over 999. Of course, this reduces to, I believe, 401 over 333, but we did not need to give a reduced fraction here, just a fraction. And either 1,203 over 999 or 401 over 333 will do.